Moha Azimlu from the University of Western Ontario. Moha did her undergraduate studies and masters in Iran for 2 years or so. But most of the master's thesis work was done, or a substantial part of it was done in India, in the IUCAA Institute in Pune. After her master's, she went to Canada to do a thesis at the University of Waterloo, with my pick, and she just started now a postdoc at the University of Western Ontario, where she is now. And she's on her way to the Knot. She's leaving tomorrow morning with Jose, who's all living at the Knot for 3 nights in La Palma. And glad to say she came here today to visit us and give us a talk on star formation in molecular clouds associated with HII.
Now, it's okay? Thank you very much. It's very nice to be here, and so thank Yuan to host me here. And I find this place very amazing to work in. So I probably should think about coming here and stay here for a long time, for at least for a few years, and the second postdoc probably here. But yeah, it's very nice to be here. And today I'm going to talk about mostly what I did for my PhD thesis. On molecular clouds and star formation within molecular clouds. Well, all of you for sure know this nice constellation, the Orion constellation, which is my favorite. This is what you see in optical wavelength, but with the naked eye, you can see the stars for sure without the lines. But if you had an infrared eye, you could see the infrared emission from the sky too. That was what you would see from the same region in the sky. There are lots of gas, mostly hydrogen gas, in the sky where mostly stars are forming within them. And as you see here, it's not just one smooth homogeneous region. It's clumpy, it has a structure inside, filaments. Some regions are hotter within, these regions are the hotter regions. And why they are hot? Mostly because when you have a massive stars form, by a massive star I mean an OB star, it ionizes the gas around itself, which we call this ionized gas, the H2 region. And so this ionized gas probably may affect the star formation within the same cloud. The H2 region is expanding. It also changes the environmental conditions around itself. So in this study, we would like to know how the formation of a massive star may affect further star formation within the same cloud. So this is a toy model of a molecular cloud. You have a big cloud. It has a clumpy structure. You have denser regions within it. And each of these clumps have a few solar mass to a few hundred solar mass, which form a few stars within it. So it fragments into smaller regions. It makes the proto-stars, and then each of these proto-stars form a star. But this could be a huge cloud, and you probably have a massive star already formed within that cloud. And the radiation from that massive star and also the ionized gas around this massive star may affect the structure of these clumps or the temperature, density, and other physical parameters within the cloud, which we are studying. So these are the outlines of my talk today. So I'm going to talk about, well, what we are actually looking for that I already described. We would like to know how the presence of a massive star and an H2 region around it may affect further star formation in the cloud. Then I talk how we selected our sample, how we measure the physical parameters within the cloud, and then some of these objects were more interesting, so I'm going to just give some notes, some specific individual objects. And then we checked out how these physical parameters have been changed in the environment. So then we studied the relation between the physical parameters like density, temperature, velocity dispersion within the clouds. And we also need to look at the stars. So we look at the infrared observation to see how the star formation has been affected by these physical parameters, physical conditions, and then I summarize the talk at the end. So as I described before, when we have the massive star, it ionizes the gas around itself. This ionized gas is expanding. It may collect mass around dense layers around itself. That star formation may trigger within these collected layers, collected mass in layers around the ionized gas, which is expanding. It also may affect the environment because of the strong UV photons, which may change the velocity dispersion, which may change the temperature of the gas around itself. It may change the density. We also would like to know if the internal dynamic of the gas around this massive star has been affected, like the velocity dispersion of the molecular gas within the cloud, or density, or we have this clumpiness has been affected by the expansion of the H2 region. And yeah, the mass function, the initial mass function also might be affected. This is a simulation by Bates and Bonner. The Jeans mass, when you have this clump, the clumps could be stable or could not be stable. It depends that if you have a balance between the gravitational force, which would like to collapse the clump, you also have the thermal pressure inside the clump, which would like to expand the clump. So if you have the equilibrium between these two forces, you have a stable region. It doesn't fragment, it doesn't collapse. But if you have any turbulence within it, if you change these conditions, or if, for example, you change the temperature here, you have a larger clump, this minimum stable mass, which we call it the Jeans mass, would be larger. Then if you have a hotter region, this hotter region is more stable against collapse. You may have a larger proto-star, and a hotter region probably may form more massive stars. And the same for the density. So Bates and Bonner made this simulation in 2005 that if you change this Jeans mass as an initial condition of the star forming region, how the formed stars as a result may change. So they started with a cloud with 50 solar mass. For one run, they had the Jeans mass equal to 1 solar mass. For the other one, they changed the Jeans mass, which is the minimum stable mass, to 1/3 of the solar mass. And this is the result of the number of the stars versus the mass, the solar mass unit. The dashed line here shows the fraction between the brown dwarfs and the real stars. So anything at the left are brown dwarfs. They are not stars. And if we compare these two plots, we see that when we have a smaller Jeans mass, we have mostly made brown dwarfs in this region rather than stars. And also the mass range is slightly different for two star-forming regions with two different Jeans mass. And the most important result was that if you look at the star formation, if you look at the mass distribution of the stars, they have different slopes. Probably you all know the initial mass function, the universal initial mass function known as the salpeter. This is the salpeter mass function, initial mass function. Mostly the universal slope that has been observed in many star-forming regions and many clusters. And in this case, the mass function, that slope is much closer to the other observed regions. But this one, in this case, is very different. So if we change the initial conditions, probably we also are changing the initial mass function, the mass distribution of the stars which are forming. This is another very recent simulation by Krumholtz et al. They also changed the initial conditions as only by density. The three columns you are seeing here are three different clouds with three different column densities. This is the low column density, the medium column density, and the high column density. What they mention here and what they take here is the feedback of the forming protostar. And they claim that when you have a protostar collapsing and it hits and radiates the thermal emissions. But if the clump itself is very dense and has a very high density, that thermal energy cannot escape and it stays within the cloud itself. So within that region, when you cannot release the thermal energy, then you have a more stable region. You have a big, massive clump which cannot fragment because it cannot release the thermal energy. And you may end up with a very massive star. So they did this simulation to show if it happens in three different density levels. So in low density, they found out that, yeah, the cloud can escape, can release the thermal energy, and it ends up in a few low mass to intermediate mass stars. In mostly a medium column density, they have a binary up to mostly massive star and just a few stars. And when you have a high density region that the thermal energy cannot escape and traps inside the protostellar region, then you end up with a very massive star which contains 90% of the total gas mass and only 1 or 2 smaller, very low mass stars. So they conclude that if you consider this density distribution, that you have very dense clumps and very dense regions that thermal energy cannot escape from that, you are forming more massive stars. So considering that conditions may change the initial mass function. When we have a very low density region or we have a very high density region, we should expect to see a different initial mass function rather than the universal saltpeter. So probably everybody knows that how the hydrogen radiates, just to have a review of everything. When you have an excited region, you have excited hydrogen like the H2 region, you have these emission lines in different hydrogen lines that you detect very easily. But this is mostly for the ionized gas and for the ionized hydrogen, or for excited hydrogen. But when you have a neutral hydrogen, you don't get these emission lines from the neutral hydrogen. So we use these 21 centimeter of the radiation from hydrogen when the spin of electron flips to another level, and the energy differences between these two spin levels create this very long emission, 21 centimeter famous emission for neutral hydrogen that we detect this to observe the neutral hydrogen. But in a molecular hydrogen, we don't have that emission. It's not excited. It's not emitting optical. It doesn't emit in this radio emission. So how we can detect hydrogen, molecular bind hydrogen? Actually, we cannot. There is no emission from hydrogen itself. It's a symmetric molecule, so there is no vibrational or rotational different levels that emits energy. So we need to look at other tracers, other molecules which are not symmetric, and they have rotational modes or vibrational modes that can emit if there is a change in these modes. And so we use other tracers to observe and study the molecular clouds. The most abundant molecule in molecular clouds is CO, carbon monoxide. Different isotopes of carbon monoxide are observed to find the structure and study the structure and emissions of the molecular clouds. That's actually the project that I have started in a nearby galaxy legacy survey that Johan and Jose are also part of this project to observe the carbon monoxide emissions from galaxies to find out where star formation is going on in nearby galaxies. This is also a schematic of our own galaxy, the Milky Way. Here are the sources that we have selected, mostly at the outer galaxy. We chose these sources mostly because we knew the distance of these sources. We need to measure the size of the clouds and the size of the clouds to measure their masses. So we selected those objects that we already know the distance for those objects. And also we selected them in the outer part of the galaxy to minimize the confusion with the background stars when we are observing the stellar component of the gas. So these are 10 H2 regions selected from the Sharpless catalog. These are optically visible H2 regions. And also we selected the ones which are small enough that we can fit them in a 7 by 7 arc minute map. And we can take enough molecular gas around them. So first we use CO observation, CO221, a very known and very abundant isotope of carbon monoxide, to study the structure of the cloud and also to find these denser regions, which we call them clumps. But CO itself is not optically thin. It's optically thick. So it's very self-absorbed. And if you look only at the CO221, you don't look at the really denser parts of the cloud where actually the star formation happens. Most of this emission is absorbed by the gas, by the envelope around itself. So what we're saying here is mostly the envelope around the denser regions. We need to use other thinner emission lines, such as 13CO, C18O, CS, and many, many other tracers that you can use to look deeper at the core of the dense regions where star formation is happening. So we use these observations to find the temperature and density of actually the core where star formation happens. And finally, we need to look at the stars because we would like to know how the stars has been affected by these conditions. We use these observations to find the temperature, density, and velocity dispersions, which shows the internal dynamic of the cloud. The line weights here shows actually the velocity dispersion. But the stars themselves are mostly embedded deep inside the cloud. These are dense clumps, which mostly, most of the young stars, newborn stars, are embedded within these denser clumps. So we cannot observe them directly in optical wavelength. So you need to use the infrared observation to detect these embedded young clusters. We used CFHT, Canada France Hawaii Telescope, to observe 5 objects out of our 10 sample. But that was, first we applied for 10, we didn't get time, so the second time we changed that to 5, and then we got time. Unfortunately, I didn't receive the data till after my defense. So it didn't come to my thesis, but I already have received the data. So this is one of the very recent data I got from a CFHT for one of our objects, and we see that a very nice cluster here. I'm going to talk about that a little more. So this is a family photo of the whole sample, 10 objects that we have, 104, 149, 152, 75, 192, and the rest. And you see that these H2 regions are very different in size and shape. We use JCMT, James Clerk Maxwell Telescope in Hawaii at Mauna Kea to make these observations. But these objects are optical ones from Digital Sky Survey. And you see that they look different in size and shape. Actually, here we have 3 H2 regions, S1, 92, 93, and 94. But if you look at these regions in submillimeter from CO emissions, they look even more different. Here, they come back. Oops. Here is the H2 region, and here you see nicely how the molecular gas has been collected in a layer nicely around the ionized gas. Here, the H2 region is a part of an extended gas. We haven't mapped actually the total of the cloud here. This one also has lots of dense clumps at the center. Here you see mostly a filamentary structure. Here are the locations of that 3 H2 regions, and you see that the gas at the center has been concentrated by pushing of 3 expanding H2 regions. So density here is really high. And so the number of stars also very, very high here. Here we mostly have missed most of the gas. This H2 region is very evolved, and it doesn't leave much gas around it. S212 also has a filamentary structure that we have mapped only half of it. But here also you see nicely, here is the location of the H2 region, but you see how nicely the molecular gas has been collected and collapsed in layers around the H2 region. This also has a filamentary structure with a twisted filament mostly at the center. These mostly 3, 4 compact objects here are very, very dense gas. These are the only ones that we have detected CS, which means the density of these regions, of these compact regions, are more than 10 to 7 particles per cubic centimeter, which means very, really high region. They could be candidates for massive star-forming regions. And this is also a very interesting one. I'm going to talk more about this nice bubble structure. So yeah, they look very different. Here you see where is the location of the H2 region for each, and how the rest of the gas is located compared to the H2 region. Okay, S104 is one of my favorite objects because it's a very, very good example of triggered star formation, where the molecular gas has been collected in layers, and we have lots of dense clumps around it. The number of dense clumps around this H2 region is more than twice than the other regions. So we have very dense regions around it, very dense clumps. And when we look at the spectrum itself, when we look at the CO emission at these clumps, we see that we have these double peaks for the clumps around it. And when we move from one side to the other side, this is just this is not an integrated map, so this is just one slice. But if you do that from one side to the other side, you see that these two peaks are coming closer together, and at the center you have only one peak, and then you go to the other side and you have two peaks. So these two emissions are coming from the one side which is coming toward us and the one side which is going away from us, which shows the expansion of this ionized gas. We calculated the expansion velocity to be about 3 kilometers per second, which is typical for an ionized gas, a few kilometers per second. And another interesting finding for that was C4 here, which I'm going to talk a little more about that later, is the most dense massive clump in this region, and it contains a young embedded cluster, which has not been detected before. We detected that in CFHD data. So probably this is a new generation of stars that are formed within the region. So we should learn that if the mass distribution and the luminosity function of these stars are that which has been triggered by expansion of this H2 region and which are probably affected by a massive star are the same as the universal luminosity function or mass distribution, or it has been affected and it's different. 212 is another interesting object. It also has these collected layers, but this cluster, which we see here, which locates here, is mostly the cluster that contains the massive star itself. It's not a new cluster. It's mostly evolved. And the massive star that has created this H2 region is a part of this cluster itself. So this is not the only one that the massive star is a part of a cluster. We are going to see that other massive stars in our study also could be, most of them are also part of a cluster. And we see the same complicated emission lines in this region as well. A triple peak, which I don't know exactly what it is, probably with just 3 different cores along the line of sight. But a little red shifted and blue shifted peaks at 2 sides of this clump, which means probably it's rotating. A side of the clump is coming toward us, the other side is going away from us, and that's why we have these 2 a little red shifted and blue shifted antisymmetric peaks here. This is one of our C4, the clumps that contains the cluster. So if we just plot, this is not from CFHD, this is because I just was very interested to see how the luminosity distribution is different in that region. This data is from 2 mass data, JHK of the band from 2 mass. So K versus J minus K shows that we have the main sequence of stars here, which is mostly the background, foreground stars. And we have a second population of stars just at the location of C4, that clump that contains this young cluster. So we really have a young generation of stars there, which are mostly giant stars. I'm not sure if you can recognize the colors. The blue squares are the giants. The black dots are main sequence of stars, and the red triangles are objects with red X's, probably proto-stars which already have accreting mass around themselves, and they have this red X's. But this data is not deep enough. So I'm waiting to reduce the CFHD data and have a nicer plot for that clump. What we expect to see from a young cluster, this also worked on a young embedded young embedded cluster by Balog, 2004. What shows that a cluster is really young is that if you have the K luminosity function, the number of stars versus the K magnitude of that cluster, the peak of the K luminosity function is brighter for younger clusters. And when they age, it just shifts to fainter magnitudes. This is a real observation, and this is a simulation for a young cluster with 3 different ages. This is one, I cannot read that, 1 mega year. But this is 1 mega year old and 3 mega years old and 10 mega years old. So as the cluster ages, the K luminosity function peaks shifts to fainter magnitude. So what we expect to see on that cluster observed in S104 is something like that. And if we can really find the peak at the exact location, we can age the cluster. S307 is another nice and interesting object, because you see a second bubble here and the second one here. So probably you had this bubble made by an H2 region, expanding H2 region first, and then you have made the second one here. It actually locates at the place of this H2 region here. This main H2 region is here, and then you have probably a second generation of massive stars formed here. And you also have the same expansion feature for the spectrum for both two bubbles here. And another interesting part is the second part of the cloud, which is far from the massive star, and probably it's not been affected much by that massive star. And you see here, we don't see any signature of expansion, just a little red shifting and blue shifting on two sides of the cloud. So probably this part of the cloud is rotating separately for itself. But it's not been affected much by the H2 region here. And the other interesting point is two stellar clusters locating at two different parts of the cloud. This one contains the massive star that has formed this nice H2 region and this bubble structure, but the second one doesn't have any massive star, and it's sitting in the second part of the cloud. So if the star-forming region for massive stars is different, so we expect to see different physical conditions for these two parts of the cloud and two different mass distributions or two different K luminosity functions for these two clusters. So this is the job written to must be done. This is one of the jobs I'm going to do, to check that how the mass distribution and luminosity function are different for these two clusters and how they may relate to the physical characteristic of these two parts of the cloud. Excel map. So that was a region, that was the cloud and stars. We need to calculate and measure the physical parameters of the cloud, like temperature, density, and velocity dispersion. But most of these clumps are not really spherical objects. They have irregular shapes, so how we can measure the size and compare them? It's very usual to define an effective radius instead of the real radius for the clumps based on the area that covers by each clump. So we define the effective radius for each clump this way. So we have the size of the clump, and we have the velocity dispersion, which is the line weight here. If we assume that these clumps are in virial equilibrium, that the internal dynamic of the cloud is in equilibrium with the gravitational force, then we can define the virial mass based on the internal kinetic energy of the clump and the size of the clump. And so we can also define the virial mass this way. But it works only for those clumps which are really in virial equilibrium, which we know most of our clumps are not. So the other mass that we can calculate for these objects are using the integrated flux of each spectrum and convert that flux to a known column density for hydrogen by knowing a conversion factor, which is known as the X factor. This X factor is the big problem in star formation, because this is an empirical relation. You don't know if this is a real number, if it changes with time. We know that it changes with time. We know that it changes in different regions, but this is an average that is, for now, it's accepted by most of astronomers, at least for galactic star formation. The problem that Johan and Jose has in intergalactic star formation is that, I guess, that you cannot believe in this X factor for every region and for every galaxy. Is that right? I guess that's the problem. So, but for galactic star formation, it's good enough to just consider that, okay, that's the X factor the average X factor for many regions inside galaxy. And so you can compare it with other regions, with other masses. And that was very reasonable for our regions too. You can also, okay, let me go back there before going there. It's worth to note that the real mass depends on the line weight square, so it depends on the internal dynamic of the cloud. The X factor mass also depends on the internal dynamic of the cloud, because if you have, for example, an expansion or any active internal dynamic for the cloud, then like an expansion or a rotation or anything, then this line is very wide. So what you're measuring for the integrated flux is much larger than the real mass that you have here. So this mass calculation also is dependent on the internal dynamic of the cloud. But is there any other way that you can do that without dependence on that, dependence on the internal dynamic? You can measure only the temperature of two different isotopes of CO, for example, 12 CO and 13 CO, or two different emission lines of CO, and assume that both of these transitions, both of these emission lines are coming from the same temperature. You can assume that these both molecules are are exciting with the same temperature, which is not a bad assumption. This assumption is called local thermodynamic equilibrium. So if you just assume that they are emitting it with the same excitation temperature, you can find that excitation temperature from one emission line, and also you need some other assumptions to just simplify this equation. And for example, you need to assume that the opacity for 12CO is very high, which is not a bad assumption. Then you can neglect this sentence here, and you can then solve the equation and find the excitation temperature and find the opacity for the other emission line and find the column density for CO, and then convert that to hydrogen. So you can use LTE model to find the column density and mass of the clump, mass of the gas as well. But the problem here is that these emission lines from CO are sometimes self-absorbed. So what we are measuring as the temperature is probably affected by the cloud itself. But which is good here, the good point here is that it only depends on the temperature. It doesn't depend on the shape or line weight or the shape of the spectrum. So it's not affected by internal dynamic of the cloud at all. S175 is one of my favorite objects again, because here's the H2 region. We observed two parts of this cloud. Which part? One part was very nearby the H2 region and the massive star. The other part was very far from it. We expected to see very different physical characteristics for these two regions. For example, we expected to see here is hotter, this colder. We expected to see more internal dynamic here. And see what happened. Some more observations of the regions that shows the ring structure of the cloud itself. Probably it's a second generation of really old stars that has formed this ring here. But it's a very small cloud separated from the foreground. This is a very small cloud with a few hundred solar mass by itself in total. This is also CO120 from 5 College Radio Observatory that was observed before. And it's interesting that here you see more observation in infrared from IRAS than here, but in molecular gas, you see more molecular gas in region B rather than A. So we observed that region in 12 CO221, which is deeper than 120, and also we have a very higher resolution here in this observation. This is region A. It's very fragmented. You can distinguish clumps very easily. The clumps are hotter as we expected because it's been warmed up by the massive star here. But then you see region B is not very fragmented. It was really difficult to distinguish clumps within it. The temperature is not really high. But it seems that the whole cloud is covered by by homogeneous gas of temperature of mostly 5 to 7 K. But if you look at the spectrum, well, that was very surprising here that region A seems to be very quiescent, a very sharp peak. The line weight here is very close to the thermal line weight, so it's not been affected actually by any internal dynamic. But contrary, region B has a very wide spectrum, and 2 peaks here and very well self-absorbed. The line width here is about 8 kilometers per second compared to that one, which is only 1. So that was surprising. If this one is close to the massive star, why this is so quiescent? And if this one is farther, why and probably is not affected by massive star itself, why it's so internal, so active? So one of the relations that you can check to see how turbulence is your region is to check that to check how the line weight relates to the size. This relation is known as the Larson's relation. That the line weight depends on the size, and you can find a relation with the slope between 0.15 and 7.7. So we find that not really good, but we find the relation for clumps for 13 CO, for 12 CO, and 13 CO, but we didn't find anything for region B. This is region A, which was closer to the massive star. This is region B, which is far and has had very large line widths. So what about these previous works? These flat lines has been observed before for clumps which are associated with water masers. But we don't think if we have water masers here, because the density is not that high to have really water masers in this region. But there was also a simulation in literature made by Chris Massner in 2007 that if you have an outflow and a protostellar outflow in the region, it may affect the internal dynamic of the cloud, such as you miss this nice Larson relation for specific sizes. If your clumps are larger than the size of the protostellar itself, then you see this the same flat lines. We don't have water masers. What about the outflow? So we checked that by observing 12 CO322 at JCMT a year after that, and we find this nice red lobe and blue lobe and outflow here, and this nice signature of protostellar outflow. So, okay, this is a part of the cloud which is distant from a massive star, but it has spontaneously star formation for itself. We wanted to check this region with a quiescent region, with a region which has been affected by a massive star, but this region itself is affected by another star forming process. So it ruined our hypothesis, actually, what we had planned for, but we were lucky because we discovered the new protostellar outflow. And if you look at the JHK data, these are from an old observation at Cape Peak. You see that at K band, oops, I'll go back. We also see a feature associated with the outflow, and also some younger stars which are only visible in infrared. Okay. What about the other objects? We checked the Larson relation, the relation between the line weight and size for other objects. And interestingly, we find that we have this relation for only 6 of the sources, and 4 of them doesn't have the relation, which 175b is one of them. So what's the difference between these two categories? We call this category 1, which has this relation, as type 1 sources, and these ones as type 2 sources. First, I had called them turbulent and non-turbulent, but then I was told by my committee that you cannot say it is turbulence that has made this difference. So I'm not going to use these two terms, but these objects here, who doesn't show this relation, have mostly larger line weights and larger velocity dispersion compared to this category of type 1, which show mostly a relation. But what was also interesting in these type 1 sources was that compared to all other studies before in the literature, the slope of the relation is much higher compared to previous job. The alpha, the parallel fitted for this data before was always is smaller than 1. At the highest level, considering all the uncertainties, is always smaller than 1. And for our object, it's mostly around 1.5. And for this region, it's even larger. So that was the first interesting point, that why we have larger slopes for these regions. We also checked the different masses that we have calculated in 3 different ways. The real mass, the LTE mass versus the real mass versus LTE mass, and we see that most of the objects most of the smaller regions, the lower mass regions, have very high real mass, but the smaller ones mostly have the similar real mass are equal to LTE mass. So we checked that the integrated mass, the X factor mass with the LTE mass, and it also shows that the integrated mass is slightly larger than the LTE mass, but it tends to be equal for larger regions again. And the same for velocity integrated mass and the, we cannot read that here, so probably you can read it here too. This is integrated mass or X factor mass and the virial mass. And you see that mostly around the 100 solar mass, the masses are equal. So it also has been observed before that for lower mass clumps, you don't see the equilibrium between virial mass and the other masses. But which means that when you have a larger clump, most of the clump is in a larger size is mostly in virial equilibrium. But when it fragments into smaller regions, the smaller regions themselves are not in virial equilibrium anymore, and they continue to collapse and form smaller regions and form the proto-stars. And we also wanted to know how the temperature, how the physical conditions have been affected by H2 region. So we checked that by distance from the H2 region. Here is the temperature, and here is temperature, here is distance from H2 region. And as we expected, the temperature should drop by distance from H2 region. But what we are observing here is the projected distance. So it's probably affected by that issue. So we also simulated that to see if you have a heating source and we have mostly the same physical conditions, the same density for the clumps, we see that for smaller regions, for smaller distances, which are smaller projected distances, we don't see much relation, but as we expect, the temperature drops by going away from the massive star. We also have exceptions here for those sources who have an internal source of energy like a proto-star. So these are exceptions here. What about the velocity dispersion? Does the internal dynamic of the cloud also affected by the H2 region? So we check that by distance from the H2 region. And we mostly don't see any relation between the velocity dispersion by distance from the H2 region. So the temperature drops, but the velocity dispersion doesn't change. The internal dynamic actually has not been affected by the H2 region itself. So if the cloud is not affected by H2 region, the internal dynamic is not affected by H2 region, but we are seeing a large line width, and we are seeing that some of the objects also doesn't have even a Larson relation, and those who have this Larson relation have a larger slope. Probably that turbulence is the initial conditions of massive star forming regions. Most of these regions already have a massive star, and they all have large velocity dispersions, which is probably the initial conditions of these regions. I'm going out of time, so I'm just going to go very quick on these final slides. As I mentioned before, 6 of our massive stars themselves are a part of a cluster, which is consistent with this belief that massive stars are forming in clusters. They cannot form individually. And the star formation efficiency also is not very far from the common and typical star formation. And these others 4, they actually have individual, just one star by itself. But probably most of these regions are evolved regions that have lost other members of the cluster. And also loss of the gas, because this star formation efficiency is not usual. So probably this region already has missed lots of gas. And I'm just going to conclusions that, yeah, we have found that layers have been collected around H2 regions. Oops, that was the end. we have found a protostellar outflow where we didn't expect to see that. We have seen a star formation has been triggered in layers collected around the H2 region. And finally, these two results that where the temperature probably has been affected by mass of the star, but internal dynamic has not. And a large line width and a large velocity dispersion in massive star forming region is probably an initial condition of these regions, which has been predicted before by simulation that you need to have turbulence in massive star forming regions to form massive stars. Thank you. I'm going to leave you with questions. Questions?
2 minutes, and I'll just ask one or two.
Sure.
The effect on a hot star on neighboring molecular stars are two effects you mentioned. One is to compress and therefore increase the density. The other is to radiate and therefore increase the temperature. Those two effects will have opposed effects on the genes. So with wind, that's the first question. Have you any evidence about with wind? The other question is that your expansion rates are very slow. 3 kilometers per second are very slow. The expansion rates of the H2 themselves are 100 kilometers per second. So presumably there is some work done by the H2 on its surroundings to slow that down before it reaches low values. Is there any evidence of that? Third question is about magnetic fields. What role do they play in governing the physical environment? So those are 3 questions.
Okay. So first question. These are all very, very important questions. The first question that how genes mass has been affected. We see that the star formation is triggered within the layers which is collected around the H2 regions. But if the mass distribution is different, I only have found one cluster. And I haven't reduced that data yet. But this is a really good thing to search that. That's actually what we're looking for, that to see how the mass distribution of this triggered cluster is different with like universal mass distribution. So yes, that's one of the issues that I'm going to check. There were previous studies, for example, in S152. A young cluster has been detected there, which is probably triggered by the H2 region itself. This was a study done by Chen in 2009, I guess. That cluster doesn't show any difference with other universal clusters. It seems to be the same K-luminosity function. They don't have the mass distribution for that one, but the color plots and the other K-luminosity functions are the same as the universal. So probably it is not a big issue, but this is one of the items I'm going to check. The second one about the turbulence and... First about the expansion. The expansion rate that we are seeing for nowadays, which is only a few kilometers per second, this is the nowadays expansion. Probably the first expansion by when the massive star was formed was much quicker than that, and it has shock fronts that has collected these layers. If this shock fronts has going beyond that, probably not. So that's why we don't see that the internal dynamic of the cloud beyond these layers are not much affected. Within the collected layers, yes, we see that the velocity dispersions are very high, and we see that the density is very, very clumpy. It's very fragmented into smaller regions. The velocity dispersion of the ionized gas? The velocity field of the ionized gas has been observed for only some of these sources that we have. For example, for 175, the velocity of the ionized gas is 5 kilometers per second compared to the rest, and the gas is 3 kilometers per second. So it's very, very similar, very, very close by. And the magnetic fields are a very important agent in star forming regions, which is very complicated. And that's why I have been neglected that here. But that's why people believe that most of these models are not correct, because they are neglecting the magnetic field. And the magnetic field is very important to keep the clumps stable against collapse. So that's why where you have the turbulence, you have magnetic fields, and this magnetic fields really helps to form more massive stars, and it changes the James mass and any other stabilities. That's correct. But it's not been studied in details because it's very complicated.
Questions? More? Anybody? Everything clear? Well, let's thank the speaker for a great talk, and thank you for the questions.
You're welcome. Thank you for having me.